Okay, now this one is kind of nasty, and it's not one I would give on a test because it takes too long. But let me just show you how I attacked this one. So I have square root of xy minus 1 over x plus 1 over y equals 2. First thing I wanted to do was write xy, the square root of xy, as a power. So I wrote that as xy to the 1/2. And then 1 over x I write as x to the negative 1. And of course 1 over y I write as y to the negative 1. Well, now I'm going to apply the derivative to each term. So the derivative, I have the derivative of xy to the 1/2, the derivative of x to the negative 1, the derivative of y to the negative 1, and the derivative of 2. Well, this one is the trickiest one because this is actually, I have to use the general power rule. Okay, so when I use the general power rule, let's think about this. I bring the power down, so there's the 1/2. Then I subtract 1 from the power, so I get the negative 1/2. But then remember what I have to do? I have to multiply that times the derivative of the inside. And so how do I take the derivative of the inside, which happens to be a product? I have to apply the product rule. So I have to apply the product rule to xy. So I end up multiplying x times y prime, and then plus y times the derivative of x, which of course is 1. So I get xy prime plus y. And so that all of that was just for that first term. Now this I can differentiate explicitly. The derivative of x to the negative 1 is minus x to the negative 2. But when you put that minus with this minus, it makes it plus. So I get plus x to the negative 2. And then the derivative of y to the negative 1, remember y is a function of x, so I have to apply the general power rule. So I get minus 1, so that's where the minus comes from. Y to the negative 2, then I have to multiply by the derivative of y, and I just have to show the derivative of y is y prime, and then the derivative of constant 0. Now here I just went ahead and wrote this xy to the negative 1/2 down here as the square root of xy in the denominator. Now here's where it gets a little tricky. Now we're getting close. We've differentiated, so now we've got to do some algebra. We got to figure out the best way to get this y prime. So what I thought I would do is I would look at all the denominators, the 2 square root of xy, the x squared, and the y squared. And I figured, well, if I multiply every one of those denominators by the common denominator of 2x squared y squared times the square root of xy, that would eliminate my denominators. So I'm just going to tell you what I did, and then you can go back and do it on scratch paper later. When I multiplied this by this term, the square root of xy and the 2 canceled. And so I was left with what? X squared y squared. And of course I also have this. Now when I multiplied 1 over x squared by this, then the x squared was canceled, and I was left with 2y squared times square root of xy, which is what I've got there. And then when I multiplied this, 1 over y squared times this, then the y squareds canceled, and so I ended up with 2x squared times the square root of xy, and then of course I still had that y prime. And of course when you multiply the 0 times this, you still got 0. Okay, so now let's take a look at the y prime. Well, before I do that, let me do something here. I'm going to go ahead and distribute x squared y squared through these two terms. So x squared y squared times xy prime is just x cubed y squared y prime, and then x squared y squared times y is x squared y cubed. Okay, now let's look for the y primes. There's a y prime there, and there's a y prime here. Okay, so I want these two terms to stay. So notice I'm going to keep those two terms over here on the left. All right, and then the two terms here, x squared y cubed and the 2y squared square root of xy, I move those to the other side, and their signs change. Well, now I can factor out the y prime. So I'll factor out the y prime, and I'm left with x cubed y squared minus 2x squared square root of xy. Now I can get y prime by simply dividing all of this mess into the mess on the right. And so now I have y prime. And so there's your final answer. So again, these can be pretty nasty. All right, now let's take a look at this right here. Now you know this is a circle. This is actually the formula for a circle centered at the 0.15 and it has radius 4. So that's what the graph. So you should know what that graph is. Now if I take the derivative, if I implicitly differentiate this, if I take the derivative of x minus 1 quantity squared, that's just going to be 2 times x minus 1. And since the derivative of x minus 1 is just 1, I don't really have anything to multiply by. And then the derivative of y minus 5 quantity squared, well, the derivative of that, use the general power rule, and I get 2 times y minus 5. But then I have to multiply by the derivative of the inside. Well, the derivative of y is y prime. The derivative of 5 is 0, so I have a y prime. And then, of course, the derivative of 16 is 0. Now, I'll leave you to go ahead and solve this for y prime. All you have to do is move this term over to the other side, and it'll become negative. Then you just divide this right here into it, and what you'll get is y prime equals minus the quantity x minus 1 over y minus 5. Now, what I want to find out where the tangent line is vertical. Well, when the derivative is undefined, that's generally when the tangent line is vertical. So the derivative would be undefined if y equals 5. So when y equals 5, the derivative is undefined. Now, if y is 5, let's go back and see what x would be. If I plug 5 in here for y, then basically this term's going to be 0, so it's going to disappear. And then I'll get x minus 1 squared equals 16. And that would, if you use square roots, you get x minus 1 is plus or minus the square root of 16, which is plus or minus 4. And so x would equal 1 plus or minus 4. Well, 1 plus 4 is 5, and 1 minus 4 is negative 3. So if y is 5, the x values that go with those are 5, 5, and negative 3, 5. Now, let's talk about where I get a horizontal tangent line. Well, you get a horizontal tangent line when this equals 0. So when would it equal 0? Well, when the numerator is 0. What makes the numerator 0? X equal 1. So x equal 1 will make the numerator 0. So now let's find the y values that go with x equal 1. Well, if x is 1, then this term is going to go to 0. So I can throw away this term, and I get y minus 5 quantity squared is 16, which I wrote right here. And then I solve that using the square root. So I get y minus 5 equals plus or minus square root of 16, plus or minus 4. So y would equal 5 plus or minus 4. Well, 5 plus 4 would be 9, and 5 minus 4 would be 1. So I get 1, 9, and 1, 1 are the places where the tangent line is horizontal. Now, if you think about it, it makes sense. You've got a circle, right? So basically, the center of the circle is right here at the 0.15, and the radius is 4. So wouldn't you have a vertical tangent line over here? And wouldn't you have a vertical tangent line over here? So if this is 1, 5, and if you go 4 to the left, you get negative 3, 5. You go 4 to the right, you get 5, 5. So that's where you get the vertical tangent line. Now, when you get horizontal tangent lines at the top of the circle and at the bottom of the circle, well, if you go 4 units up, you're going to get to 0.19, and if you go 4 units below the center, you're going to get to the 0.11. So it really makes sense that, you know, the points where you're getting vertical tangent lines are the left and rightmost point of the circle, and the points where you're getting horizontal tangent lines are the upper and lowermost point of the circle. All right, let's do some implicit differentiation with trig functions here. All right, so let's say you have sine of y equals x. Okay, well, if I apply the derivative of sine y with respect to x to both sides, and I have to take the derivative with respect to x to both sides, well, the derivative of sine y, well, the derivative of sine of a function would actually be cosine of the function. But remember, you have to multiply by the derivative of the argument, and since I don't know what y is, I have to assume that the derivative of y is just going to be y prime. And now the right side's easy because the derivative of x with respect to x is 1. So actually I get, if I solve this for y prime, I get y prime equals cosine of y. Now what's interesting though is sine is opposite over hypotenuse and x is opposite. Let's see, so x is opposite and 1 has hypotenuse. Okay, so in other words, what I'm saying here, the sine of y, let me stop this and okay, so what I was trying to say here is that up here it says that sine of y is x, or x over 1. So if you draw an angle here, let's say this angle's y, then sine is opposite over hypotenuse. So the opposite would be x, hypotenuse would be 1. And then the adjacent side, using the Pythagorean theorem, I can just get the square root of 1 minus x squared. Well, this says 1 over cosine y. So I can actually figure out that cosine y is actually adjacent. So cosine of this angle would be adjacent over hypotenuse. So it would be this over this. But y prime is actually 1 over that. So 1 over that would actually be 1 over the square root of 1 minus x squared. And this comes in handy for inverse trig functions. So it's just another way to write it, the derivative. Okay, here's another example. I have cotangent y equals x minus y. Well, we know the derivative of cotangent is minus cosecant squared y, but using the chain rule, I would actually have to multiply by the derivative of y. And then the derivative of x is 1, the derivative of y is just y prime. So now if I move the minus y prime over here, I get y prime minus this term. And then I can factor the y prime out, so I get y prime equals 1 minus cosecant squared y equals 1. And then you can just say, well, y prime is equal to 1 over 1 minus cosecant squared y. And, well, 1 minus cosecant squared is minus cotangent squared. So this is actually 1 over minus cotangent squared, which 1 over minus cotangent is actually minus tangent squared. Okay? Well, let's just summarize this one. Here, if you take the derivative of this is going to be 2x. The derivative of this is going to be 2y prime. The derivative of this, you're going to have to use the product rule. So you get xy prime plus y. And if you do some algebra here, just work some algebra here, and what you're going to get is you're going to actually get, let's see, you're going to get 6y prime minus 10xy prime equals 10y minus 6x. That's supposed to be a 10, not a 100. So anyway, 10y minus 6x. Long story short, you'll be able to get these two terms together over here, and then you'll be able to get these two terms over here, and then you can factor out the y prime and solve for it. Now, I wanted you to find the derivative of this, of the slope at 3, 1. So basically here, wherever there's an x, I got to put in a 3, and everywhere there's a y, I have to put in a 1. And when I did that, I got 1/3. Now, there's another example here that you can do. You can practice on this one. And notice I wanted to find the slope of the tangent line here at the point square root of 2 minus 1 over square root of 2. And notice I found that the slope was 1/2 for that. So you can actually, these are actually some interesting graphs. If you look at these graphs, you'll see that the first one looks just like a couple of crossing lines. And so the point 3, 1 was right here, and you had a slope of 1/3. And the other one, the point that I was interested in, was right here, and you had a slope of 1/2. And I want to end this section with showing you a few interesting graphs. Just for fun, show you a few interesting graphs here. So here's 4 interesting graphs that you can look at, and they have kind of weird names. This is the Witch of Agnesi. This is called an asteroid. This is called a cissoid, and this is called a cruciform. And you'll find that there's a lot of graphs with other names that you could look up if you wanted to. And that's pretty much it on implicit differentiation.